It would be coming out of a sort of, let's say, new golden age in the rapidity with which humans can discover stuff that previously we had to sort of grope in the dark for.
Welcome to Futuremakers, your invitation to cutting-edge debates on our changing society. I'm Peter Millican, Professor of Philosophy. Thank you for joining me for this special one-off episode on quantum computing. After hearing from colleagues like Professor Simon Benjamin, I decided to step outside Hertford College and search among the famous spires of Oxford to discover the truth about the race to develop the world's first truly scalable quantum computer. I met a wide range of researchers who gave me their thoughts on the powerful next realm of computation their work opens up, via the fundamental building blocks of quantum computer to the ultimate goal of a truly universal quantum computer. But is it right to think of this as a race? Will we ever reach the goal of a universal quantum computer? And what would it mean for our society if we did?
Quantum computing fundamentally is the best way to process information based on the laws of physics as we know them. If you talk about it from that point of view, it sounds like, wow, this is surely going to change the world.
I had constructed what I thought of as the generalization of the universal Turing machine in quantum formalism. I proposed this thing, what we today call a universal quantum computer, and realized that it was more powerful.
We have the equations, so I could put on my whiteboard the equation that tells you whether or not two molecules will react with each other. But we can't actually use it to predict things because it's just too complex to do that task. So it's a strange situation. You know the rules of the game, but you can't actually play the game because it's too complicated.
Those were Oxford professors Peter Leake, David Deutsch and Simon Benjamin sharing their belief that quantum computers could have a huge impact on society. But how did we discover that quantum mechanics could offer such developments in computing? And why did this realm remain hidden for so long?
We believe that the world around us behaves according to the laws of classical mechanics, and it took us hundreds of years to work out that actually something else was going on deeper underneath. Why was that? It's because the quantum nature of matter hides itself. It washes out, so we get the familiar kinds of structures that we're used to, described pretty well by classical mechanics, Newton's mechanics.
That was Professor Chris Timpson, philosopher of physics. Quantum mechanics arose at the turn of the 20th century, when theories were put forward to explain new observations that couldn't be explained with classical mechanics, such as Max Planck's formula for observed black body radiation, and Albert Einstein's account of the photoelectric effect. Quantum mechanics was able to give a mathematical formalization of the uncertain, probabilistic, wave-particle nature of subatomic particles that physicists were beginning to observe through these experiments. By the 1920s, due to the work of many physicists, including Niels Bohr, Werner Heisenberg, and Erwin Schrödinger, quantum mechanics had become the standard formulation for atomic physics and was widely accepted as a field by the end of that decade. Schrödinger and Einstein, however, were not entirely happy with the counterintuitive nature of quantum superpositions, according to which a quantum system, such as an atom or photon, can exist in a combination of multiple states with many different outcomes. To highlight the apparent absurdity of this on the everyday scale, Schrödinger proposed the following setup, which he himself described as quite ridiculous. First, we have an atom of a radioactive substance, which may decay at any moment, emitting an alpha particle. Next, a murderous device, such as a fragile flask of cyanide, linked to detection of the alpha particle. And finally, a cat, which will then be killed by the device. And all of this would be hidden in a box, concealed from any observer.
Quantum mechanics says that there isn't any fact about, at the microscopic level, when or whether, indeed, a particular nucleus is going to decay and emit an alpha particle. And you might be able to put up with that at the microscopic level. You say, look, we can't see the thing directly, and it's just sort of doing its crazy thing, but it's business as usual out here. But then Einstein pointed out that, well, we shouldn't necessarily be happy with that, because we can amplify that fact that it's indeterminate whether or when the atom decayed from the microscopic level where we can sort of ignore it, up to a level where it really is going to make us anxious.
According to the quantum mechanical description of Schrödinger's setup, Until it's been observed, there isn't a fact of the matter whether or not the atom has decayed. So there also isn't a fact of the matter whether or not the murderous device has been activated. So there isn't even a fact of the matter whether the cat is alive or dead.
But surely there ought to be facts of the matter about whether cats are alive or dead. Now we can take that into a computational realm by saying instead of thinking about things like cats, think about the values of bits in a memory register. We're used to thinking of bits in terms of noughts and ones. We use particular distinct states of our memory, whatever it is, to represent these different logical states. But if we believe that quantum mechanics is the correct theory for describing the underlying material that we're dealing with, we say, well, look, there are more states that the thing could be in than just naught or one. Just like the cat, which can be alive or dead, or it can be in between in a way that's indeterminate between naught and one.
It took some decades, until the late 1970s, until colleagues here at Oxford were able to make the leap from Schrödinger's cat to the computational potential that was hidden in the quantum realm. At the time, physicists were arguing over theories about what's known as the wave function collapse. Or in other words, why an observer would always see the cat as determinately either alive or dead, and not see the superposition of states in between. David Deutsch of Oxford's physics department made the key breakthrough in what became a landmark paper on the universal quantum computer.
That paper was rejected by Physical Review. This was in something like 1977. It wasn't published until 1985. My boss at that time was John Wheeler, who was very much opposed to the Everett interpretation.
Hugh Everett was a leading proponent of the many worlds interpretation of quantum mechanics, which denies the actuality of wave function collapse, and instead views the experimental setup as going different ways in lots of different parallel universes. So Schrödinger's cat remains alive in some of those universes and dies in others. The theory may seem crazy, but it has some nice theoretical virtues, and its observable consequences have generally been thought to be exactly the same as those of the more traditional formulations of quantum mechanics.
And I thought of a thought experiment, contrary to what everyone had said, including Everett up to then, which could distinguish in principle between the parallel universes interpretation and the single universe interpretation, thus making them not interpretations, but different theories. To make this thought experiment work, it required something to stand in for the observer, which appears in the non-Everett way of doing quantum theory. So you could have a computer being that, and it would have to be a universal computer, so it would have to be able to do anything that any other physical object could do. I proposed this thing, and this thing was what we today call a universal quantum computer. But I didn't think of it like that. I thought of it as just a physical object which was going to be used in this thought experiment. At first, I didn't know that this would be useful. In fact, I guessed it would not be useful. But it was just a mode of computation that classical computers couldn't perform.
Classical computers operate by storing information in what are called bits, essentially on-off switches. We can think of each bit as storing a binary digit, either 1 or 0, so that a set of, say, 8 bits, known as a byte, can store a single 8-digit binary number. The more bits we have, the larger the range of numbers we can store. But I understood that the fundamental element of a quantum computer, called a qubit, works rather differently. And to find out more, I caught up with Chris Timpson and Tyson Jones at Oxford's Quantum Nosh, a winning combination of chatting quantum computing and cake.
The way in which your quantum bit, your qubit, is going to behave computationally, yes, there are ways in which you could prepare it in a naught, there are ways in which you could prepare it in a 1, but there's also an infinite number of ways in which you can prepare it in between, where it's neither naught nor 1.
That's the very, very basic necessity of a quantum computer, that whatever you choose to represent your bits, they can enter uniquely quantum states, or qubits.
But how can such quantum bits give us potentially more computing power than a standard or classical computer? Professor David Lucas visited me here in the Hobbs room to explain more.
If I have a single binary digit, there are 2 possibilities, 0 or 1.
That's 1 bit.
That's 1 bit. If I have 2 bits, there are 4 possibilities. Both can be 0, both can be 1. First bit can be 0, second bit can be 1, or vice versa. There's 0, 0, 0, 1, 1, 0, and 1, 1. A quantum computer has qubits, which also have those same two states, which we label as 0 or 1. And the interesting difference here is that a 2-qubit quantum memory can store all those 4 possible combinations and manipulate and work with them at once. This is not the whole story about a quantum computer. I should make clear about what makes it powerful, but it is an important part of the story. So if I have 2 qubits, I have these 4 different states. If I have 3 qubits, you write down the possibilities, I have 8 possible numbers. And whereas a conventional computer can, if it has 3 bits, can store only one of those 8 binary numbers at a time, the quantum computer stores, in a sense, all at the same time. If I have 10 qubits, I've now got 2 to the power 10 possibilities, which is 1,024 numbers. That's the exponential scaling. Every time I add a qubit, I get twice as many numbers. What if I had, say, 300 qubits under perfect control? If you have 300 digits, then the number of different states the system can be in is 2 to the power 300. That's a very large number.
Extremely large.
That number is in fact larger than the number of atoms in the known universe.
A lot larger.
So that means if I wanted a traditional computer that had to be able to store all those numbers, I'd have to use every atom in the known universe.
Now that I had the idea of the exponential computing power that a qubit could offer, I wondered what the other main building blocks of our quantum computer would be.
At the most simple level, you need a register which you can prepare in certain ways. You then need to be able to let it evolve under its natural quantum evolution. In other words, you need to fix what quantum algorithm you wanted to implement. And then as part of doing that, or as part of preparing to read out the result, you're going to need to transmit your quantum information from one place to another whilst preserving its quantum features. And all of those elements for building a quantum computer are really challenging, but delightfully challenging, but they're really challenging because you need to keep it all quantum. It's very easy to lose that quantumness.
In the year 2000, the American theoretical physicist David DiVincenzo identified several criteria necessary for constructing a quantum computer. David Lucas again.
We need these 2-state quantum systems, and we need to be able to manipulate individual qubits independent of each other. We also need to be able to do operations between multiple qubits. At a minimum, we need 2-qubit logic gates between arbitrary pairs of qubits in the system. We obviously need to be able to initialize the state of the qubit, to put the information in, if you like, to my computer, and we need to be able to read the information out. We need to be able to read the information out both for the final answer, of course, of our calculation or algorithm, but more importantly, really for correcting the errors and doing the quantum error correction as the calculation is in progress. We need to be able to read out some of the qubits, correct the other qubits, and so on. The qubits need to have sufficiently long decoherence time, by which I mean the time a given qubit will stay in a particular quantum superposition state I want it to be in. That time needs to be long compared with the time it takes to do the individual operations that we need to do, like the gates and the readouts and so on, and the error correction. And we need to do all these operations with sufficiently small errors, ultimately, that we can implement the ideas of error correction. And that by sufficiently small errors, we need 0.1% or 0.01% error levels in practice.
Achieving error levels like this may be relatively easy in classical systems, but in the quantum world, it's fiendishly hard, owing to the difficulties of manipulating qubits without destroying their quantumness. Here's Dr. Natalia Aries.
Quantum objects in general, particularly for quantum computers, you have to find a sweet spot because you want for a quantum system to remain quantum for a long time till you make all these operations. You have to keep it quantum, meaning that you have to isolate it from sources that might make it lose its coherence, right? So you want an object that is very isolated, but at the same time, if it's very isolated and it lasts coherent for very, very long time, it also means that it doesn't interact much with the with the environment. And then how can you control a quantum computer or a quantum object that is so isolated? So you need to find the right balance between how isolated this object is and how well and how fast you can control it.
So I asked Simon Benjamin, how far have we got towards developing each of these aspects of a quantum computer?
There are a number of different candidates. Back sort of in the early days, a lot of especially physicists responded by saying, well, you know what? The stuff I work on in my lab sounds like it might be what you want. And so people worked through very carefully how they could take sort of physics experiment A and turn it one day into a computer. And as a result of that, we have several completely different ideas for how to build a quantum computer. It's a physics experiment if some interesting phenomenon can be seen and you can describe it and then you write it up. It's a technology if it works every time and it's very reliable and precise. And this is a difficult gap to close for quantum systems because they need to be isolated from the world very perfectly and they're tough to control. Which means that in the lab we can get a few qubits working in whichever is your favorite widget. But it's not clear in many cases how to take that and turn it into a machine that might have millions of qubits that you may need to solve certain kinds of problems.
One leading candidate for a scalable qubit is a trapped ion system. Here's David Lucas again.
An ion trap is essentially a device that allows you to trap charged particles, charged atoms in our case. We often work with calcium atoms. When you take a single electron of calcium, it is charged, becomes a calcium plus ion, and it can be trapped in a vacuum using electric fields. Right. So we have electric fields which trap the ions, and then we've got single atoms essentially that we can then manipulate with lasers.
And the important thing about it being an ion of calcium rather than an atom is that you've taken an electron off, so it's actually positively charged, and that's what enables you to move it around and manipulate it. Is that
It
right?
enables it to be trapped by electric fields, that's
Yes.
right, and it can be then moved and manipulated. But a lot of the manipulations of the quantum state of the atoms are done with either laser fields or microwave fields in our experiments.
And what sorts of manipulations are possible there?
We can initialize the atoms to a particular internal state. So, as you're aware, atoms, if I take the simplest atom, hydrogen, there are certain quantum states of energy which the atom is allowed to be in. And in our calcium ions, we take the two lowest energy states as our two different qubit states, and we can, as I say, initialize those ions in a particular state using a process called optical pumping with a laser beam. And we can manipulate the qubit, put it into arbitrary superposition states, again with carefully controlled pulses of a laser, and we can even control the motion of the ion using laser pulses, because light has momentum, and that's what allows us to couple to the motion of the ions and do these multi-qubit gates. Because when I have two ions in a trap, they're a little bit like two masses joined by a spring, and this the oscillatory motion of those masses in the trap they're coupled together because they're charged particles. So when one particle moves, it affects the other particle.
I see. So you're using the energy states of the atoms to record the information.
That's what stores the quantum information. That's correct.
And the motion of the atoms, or the mutual motion, to perform the logic gate operations.
That's correct.
Ingenious. I caught up with Vera Schaefer at the Quantum Nosh, where she explained the key strength of trapped ion systems, that they are highly reproducible.
They're identical all over the universe. So if I have a calcium atom here in Oxford, it will be exactly the same qubit as a group in the US working with calcium. And that's really useful because my quantum computer, all my qubits have to behave exactly in the same way.
I think that's a big advantage because one doesn't have to worry about the fact that each of the elements, each of the blocks of the computer have to be the same.
Controlling trapped ions with electromagnetic fields, however, does cause some problems.
Magnetic field noise is one of the largest sources of decoherence for trapped ion systems. For example, if someone moves the elevator in our building, which is a huge blob of metal, that will decohere our qubit.
The big catch in quantum computing is that business of needing to control those qubits perfectly. Of course, in the real world, nothing is perfect. And one of the big stumbling blocks going back 20 or 30 years to the original ideas of quantum computing is how do we deal with errors in the system? Peter Shaw, working in the States, and Andrew Steen, working here in Oxford, they discovered something called quantum error correction. In essence, a way to find out about the errors in the system, in the qubits, without measuring them directly. And it's, in my view, the biggest breakthrough in the field since the idea of the quantum computer in the first place. It's the idea that turned it from a cute theoretical idea on paper that would interest mathematicians but could never be built to something that could be practically feasible.
How far has this gone? How many qubits can be put together and error corrected in the current state of the technology?
Well, I'm going to stop you immediately there, Peter, because I don't like the question of how many qubits, because it's already an oversimplification. What one cares about is not just the number of qubits, but the quality with which we can manipulate them, the quality of our operations and control over them.
This technological challenge reminded me of the early development of the classical computer, when quality of performance was a crucial issue and a number of different switching mechanisms, relays, valves, transistors, and finally integrated circuits were developed in turn. Which technology, I wonder, is going to provide the basis for a robust and workable quantum computer? Here's Peter Leak.
The two currently thought to be the leading platforms, trapped ions and superconducting circuits. Superconducting circuits is one of the younger platforms for quantum computing, but it's grown very fast.
Qubits using superconducting electronic circuits take advantage of the behaviour of electrons moving across a device known as a Josephson junction, essentially two superconductors separated by a thin insulating barrier. Having cooled them sufficiently, it becomes possible to observe discrete quantum states relating to the phase, charge, and flux of the system. But a disadvantage of this approach is that even in the best manufacturing settings, no man-made systems will ever achieve the precision of using single atoms, which are, by their very nature, identical to each other.
Of course, if you make a model and you draw it on a piece of paper, it looks like that's all going to work perfectly, but then you try and build it and you realise, oh, actually, when we build a thing out of stuff, it's not perfect. There's slight asymmetries here and there, there's a bit of friction here and there, and it turns out that the slightest error propagates so badly that the whole thing just fundamentally doesn't work.
Improvements in manufacturing and the ability to manufacture in bulk and then select the best qubits means that superconducting loops are beginning to compete with ion traps as a potential basis for early quantum computers.
People talk about this coherence time, so this kind of length of time that your qubit is quantum and useful for quantum computing. The coherence time was something on the kind of nanosecond timescale. Over 20 years, the coherence times have gone from the nanosecond timescale up to approaching milliseconds. Nobody's got circuits where everything's sort of around about the millisecond yet, but 100 microseconds is seen in quite a lot of circuits around the world now.
Researchers here at Oxford are also looking into other, more exotic ways to build qubits. I met with Professor Jason Smith, who told me about his fascinating approach involving creating vacancies in diamond lattices.
We take a laser and we focus it inside a piece of diamond so that the focal spot is nice and small, it's a few hundred nanometers across, and then we deliver pulses of energy such that there is enough energy which is absorbed into the diamond lattice that it can dislodge carbon atoms and move them out of their positions within the diamond lattice to create vacancies.
Jason went on to explain that as nitrogen is the most common impurity in diamond, nitrogen vacancy centres, or NV centres for short, often form in these point defects within the crystal structure. The electron spins at these NV centres can then be manipulated with electromagnetic fields or light, causing resonances in the light emitted by the NV centre, and suggesting that they could be used as the basis of a quantum computer.
It is a very different process, however, doing the engineering of the diamond material. Essentially what we need to be able to do is to be able to create these NV defects where we want them inside a piece of diamond, and ultimately we would like to be able to have some control over this interaction between the electron spin on the NV centre and a nearby nuclei.
One great advantage for researchers in Oxford is the opportunity it gives them to learn from other groups, operating not as rivals, but as colleagues.
The architecture for a quantum computer that we're aiming towards with Diamond is very similar to that which our colleagues in Oxford are aiming towards with ion traps as well. So this idea of an optically networked set of matter qubits.
Another competing material, which we understand very well and use in most of our modern technology, is silicon. Here's Natalia Aries again.
Of course, I'm biased on what I'm going to say, but I think they're a very serious candidate because we know how to do these objects. They are in our phones, and even very similar devices to the integrated circuits that we produce nowadays. If you cool them down, you can see quantum behavior.
By now, I'd heard about quite a range of technologies being used to develop qubits here at Oxford, but I had to wonder, why isn't there a clear front runner? I asked Tyson Jones more about the challenges of building the perfect qubit.
You have these two opposing requirements. I need to make sure they don't talk to the environment, but that they do talk to each other. It's really hard to prevent classical noise, even just thermal energy, getting into your quantum computer. This is just an engineering problem. It's currently really, really hard to do this, and that's why there are so many different architectures. Semiconductors, quantum dots, ion traps, superconducting circuits, all these different architectures for a quantum computer, none of which we've validated yet because the task itself is just so extremely difficult.
David Deutsch explained to me why quantum computers need such sophisticated error correction, far beyond the level we find entirely adequate for classical computers.
All classical methods of error correction involve basically making redundant copies of the computation. Like in a transistor, like in a computer, a 1 or a 0 is represented by billions of electrons. And you kind of take the average and then reset them to the average. And now that operation destroys quantum coherence and therefore places a fundamental limitation on what quantum computations can be done in real life.
In addition to building scalable networks of qubits and developing suitable error correction systems, Oxford academics are also leading efforts to develop a universal quantum programming code. According to Jamie Vickery, the language of quantum computers could be influenced from a quite unexpected direction.
Turns out that all the abstractions that we developed for high-level classical programming are completely useless. Loops don't really exist on a quantum computer. Variables don't even really exist on a quantum computer, because in a classical computer you have a variable, say x equals 2, and then you can use x in lots of different ways. But if that x is now a quantum variable, it turns out that you can only use it once. You might say, well, let's just copy that quantum variable x. It turns out that quantum information can't be copied. So the very notion of a variable, as we're familiar with it in classical programming, becomes completely useless. And it's a big problem. So we can then say, okay, what's going wrong here? Why doesn't quantum information speak this language that we've developed over 80 years of the development of modern computer science? And one possibility is that it's because quantum information, in fact, doesn't really speak the language of logic as we've come to know it and develop it. What it speaks is the language of geometry.
As I understand this, quantum information speaks the language of geometry because superposition involves the addition of vectors, like following a sequence of arrows around a space, rather than adding simple numbers. Earlier, David Lucas and I had discussed how this potentially gives vastly more power than a classical computer. Along this journey, I'd heard repeatedly about the prospect of so-called quantum supremacy, and went back to Simon Benjamin and Jason Smith to find out more about this exciting sounding future.
Crossing over this 50-ish qubit threshold is called the quantum supremacy threshold, and the trouble is the word is used by people who don't understand what it means and just get excited by the word supremacy. So it sounds like if you're an investor, you can invest in a field, surely once a machine has achieved quantum supremacy, it must be worth a fortune and doing amazing things. No, it's just into uncharted territory. It might still be useless in practical senses until it reaches some higher number, like 200 qubits. Maybe that's where the first really valuable applications live. We need to be careful, I think, as a field, using the right language, because we can burn out. People might get overexcited that in the next 2 years, incredible machines are going to emerge that solve everything. We certainly won't have a mature stage quantum computer in 2 years. We might start to have these machines that are useful for something, but we won't have the millions of qubits behaving themselves nicely that we would need to say we've reached the mature version.
The current understanding from our theoretician colleagues is that in order to make fully fault-tolerant qubits, you are likely to need many, many individual physical qubits to be able to perform the kinds of error correction algorithms and to make a fully fault-tolerant computational qubit. The numbers depend very much on what your fidelities are for your logical operations, but the kinds of numbers we're looking at the moment are 1,000 or so physical qubits in order to be able to create a fully fault-tolerant qubit.
Realistically then, how far are we along the journey to develop a genuinely useful quantum computer? Professor Andrew Briggs told me that developments around qubits now were a little like the early development of the aeroplane.
Nobody went straight from the Kitty Hawk to the 747 commercial plane, there were many intermediate stages. It may be that the first quantum computer is not the eventual quantum computer. I think that's more than likely.
Suppose we compare this work towards developing a quantum computer with the early work to develop the classical computer. From that perspective, are we closer to the analytical engine of Charles Babbage or to Alan Turing's monumental breakthroughs? Simon Benjamin.
I would say that we are past the Babbage stage of just having a good idea and hoping it will work. But we're not quite at the sort of World War II levels of building machines that actually are effective. I would hope that we're nearer to Turing than we are to Babbage. Partly because Babbage's idea didn't work.
If we've got a way to go, is there a race to get to the world's first scalable quantum computer?
The word race implies that there could be multiple winners, and the one that wins will just be the one that performs the best. We don't know if that's true of quantum computing. We know that several different approaches could make a quantum computer, but it might be that in hindsight, when we understand things more clearly in 10 years' time looking back, we'll realize that actually ion traps had such advantages that it really would have taken immense effort for any of the other approaches to be a scalable quantum computer competitively. Just like the Babbage engine, we could build it now, but we're not going to bother because it's just so much better to build out of transistors. It might be the case a bit more like a sort of standards conflict between, two different technologies for recording music or something. They actually both do a great job, and there's not much to choose between them. It's just a question of which one gets there first and brings the product out more successfully. That one will be the dominant one. So we don't know which scenario is the case. Maybe there's very little to choose between silicon and superconducting devices. It's just a question of who gets their act together first and gets the product out there, and then everyone starts to lock into that and says, yeah, this is how we do it. It's certainly a competition. It might be a race. We kind of treat it like it's a race, but still in a pretty collaborative way. No one is, to my knowledge, trying to push the other guy back.
And Peter Leake again.
I really think this is a much bigger thing than a single winner race. This is like a complete game changer in how we process information, which is at the heart of humanity's development. I think it would be surprising if just like one company did all of that, in the end, or there was just one particular way of doing that, and that was it.
We heard earlier about American mathematician Peter Shor's work with Andrew Stein around quantum error correction. But Shor is also responsible for one of the algorithms that could be a key driver in the race to develop functional quantum computers. The so-called Shor algorithm solves the following problem. Given an integer n, find its prime factors. Given that our most widely used encryption key scheme, the RSA scheme, assumes that factoring large integers is too difficult in real time even for the best supercomputers, we're now seeing efforts from many companies and governments, similar to the wartime efforts to break the Enigma code, as they invest heavily to be the first to develop a quantum computer sufficiently sophisticated to run Shor's algorithm.
NIST started their standardization process back in 2016.
That's Ali El-Kafarani. NIST is the American National Institute of Standards and Technology.
They actually predicted that by 2030, with $1 billion, you will be able to build a quantum computer that can break the public key infrastructure.
If we're not yet near the stage of having a quantum computer that can run Shor's algorithm, is this something we really need to worry about now?
It works in retrospect. So are you happy with all your personal details, health records, financial records being publicly available in the next 5 years, 7 years? If you're happy with that, then yeah, you might not be in trouble. But if you're not, then you are in trouble from now, because you really need to switch to the new generation of classical cryptography, which is called post-quantum cryptography, that relies on different math that happens to be, not vulnerable against quantum computers.
Are there any sectors particularly at risk?
The health and financial, for different reasons. Health is about privacy. You don't want to reveal anything about your health record, not in the next 5 years, in the next 15 and 20 and 25 years, right? Which makes it a weak spot for others that might use those information. And also the financial sector, because there the information, are far more important to corporates and businesses and those who have deals that they don't want to reveal, in the next 5 or 10 years, etc. There are sectors that are not even good, at using the current crypto systems that we're using. So these are the sectors that I'm really worried about.
So with many nations and companies believing that a quantum computer is inevitable and investing heavily in their development, what do our researchers think? Natalia Aries, Tyson Jones and Jamie Vickery share their somewhat contrasting thoughts.
It's just too early to say, what the winning realization is, who's going to laugh the last, and, it's just too early to say.
Any day now, someone could write a paper that shows, in principle, due to these other considerations, practical quantum computation is impossible. This hasn't been ruled out. We haven't proven it must eventually become feasible. Any day it could be shown to the converse. So that's a bit scary.
At some point in the future, it will have become clear that we've cracked it, that we've got a powerful physical basis with which we can build quantum computers.
But if Jamie is right, and the world of quantum computers is just over the horizon, what will this world look like? Will the quantum computer become as ubiquitous as the classical computer is now? Simon Benjamin doesn't think so. He believes that quantum computers offer an additional option, not a replacement.
Qubits will never be as robust at being bits as our conventional technology. So you will still be horses for courses. It will still be the case that if what you want to do is add up a series of numbers, which a quantum computer won't do more quickly than a conventional computer, you should use a conventional computer for that. I wouldn't expect quantum computers in our phones, because many of the best ideas for quantum computers just don't fit in a phone. They need to be in the special circumstances like low temperatures or high vacuum and so on.
But how will quantum computers change society?
This is going to change the world, right? I mean, even if all it does is enables us to design a battery that's 20% more efficient than all the others before, that already changes the world.
It will be a different world because of the manifest control we have over the microscopically small. That will manifest itself in, I think, extraordinarily various ways in technology. The fact that we can control individual quantum systems with such grace and precision is going to make a difference across the board.
I think the thing that excites me the most is this idea that we might find ourselves living in a golden age of rapid discovery.
What role will they take? Initially, they will be servers, they will be living in some data center somewhere, and we will send off computations to them. Computations like optimize the shape of this aeroplane to minimize friction, or find the best route for me to drive home, or hack into this secret code, right? We will send these problems away to a quantum data center to do the computation. It'll send it back to us as an ordinary classical message. But there's no reason to think that over time this technology wouldn't be miniaturized and eventually be something that we have in our homes or even in our pockets.
Quantum computers could also have a transformative effect on drug design and discovery. At present, simulating the behaviour of atoms and molecules is incredibly processor intensive, with even the interactions between just 3 or 4 particles being devilishly complex to model, meaning that today's supercomputers are only able to simulate molecules up to around 100 atoms in size. Quantum computers offer the potential for far more efficient calculations, which could prove truly transformative, according to Simon Benjamin.
In, for example, drug discovery, or even in combating diseases where it's a spreading disease, if we could take the trial and error out of the human discovery process, or even just make it a lot less trial and error using a quantum computer, suddenly you'd have access to much better drugs, better materials, things like that. It would be coming out of a sort of, let's say, new golden age in the rapidity with which humans can discover stuff that previously we had to sort of grope in the dark for.
As new pharmaceutical compounds typically contain thousands of atoms, way beyond the most sophisticated compound we can simulate today, I asked Tyson Jones how a quantum computer might transform everyday work in the lab.
So maybe now the lab assistants who are currently going through these many drug designs for pharmaceutical companies will instead be programming on their quantum computer to inform the next generation of drugs.
And it's not simply the direct effects of a fully scalable, fault-tolerant quantum computer that interest researchers here at Oxford, but the exciting prospect of what they're calling the post-quantum world. Here's Chris Timpson.
So there's an idea of what we might think of as a post-quantum world, that is one in which we see the rules of quantum mechanics that we've worked with such enjoyment and endeavour for the last century or so get replaced with some future rules that take us not back to classical physics, because we've seen that can't be done given the so-called no-go results, but that in some ways go more quantum, that take us further down the route of embracing the difference from classical physics and push us further down the line.
The ability to control the incredibly small in the quantum world may also inform some really big questions. Natalia Aries, Andrew Briggs and I discussed how with small enough masses, held close enough together, we could start to learn more about one of the fundamental forces we understand least: gravity.
You usually think that for gravity you need big things. If you make things close enough together, then you can do significant experiments with very small masses. And now, at last, you have the prospect of doing laboratory scale experiments that might help to address these two irreconcilable great theories of the 20th century.
And actually, as well, quantum mechanics is all about measuring quantities with very high precision, making a bigger effort in the accuracy with which we can measure some quantities. We could probably start realizing that there are these gravitational effects that we've just been overlooking, and we don't know what we're going to find.
And what we're trying to do is to say, well, if you've got two objects with a gravitational field between them, is the field between them classical, the sort of thing that would have been understood by 19th century physicists like James Clerk Maxwell? Or is it quantum, the sort of thing that, was built on insights of people like Planck and Einstein and others who came after, and it's quantum in the same way that photons are quantum? Nobody knows the answer to that question at the moment. And the amazing thing is that with laboratory scale experiments here in Oxford, we may make progress towards an answer.
Simon Benjamin suggests that quantum computers could even help us understand how we think.
It has been speculated over the years that the human brain might have quantum stuff going on inside it. And the general sense, including my view, is that it doesn't. That is another debate. But it may be that harnessing quantum physics and using those computers will help us to be able to produce artificial general intelligences, or things that start to be a bit more like a mind.
Or, says Chris Timpson, the complexities of black holes.
But it turns out that there's some kind of intriguingly rich analogies, or what may be more than analogies, between the kinds of behaviour that one sees with evaporating black holes and how one would think about the flow of information or the structure of entanglement within a quantum computer. There's even thoughts that some ideas from error correction might give us the key to understanding what's going on inside the black hole, where all the information about the quantum matter that falls into the black hole is stored. It's puzzling because as the black hole gets smaller and smaller as it evaporates, there's less and less space for all of the information that you think ought to be in there. And you think, where did it all go? That's one of the key puzzles. And ideas from quantum computation, from quantum information theory, can be usefully deployed, surprisingly, in that kind of area. It gives you ways of thinking about systems which you wouldn't obviously do before.
I must say, it's been an absolutely fascinating trip into the world of quantum computers, and it's going to be very exciting following my Oxford colleagues' endeavours to create the world's first truly scalable quantum computer. It's only left for me to thank them in full for their time. So thank you to Peter Leek, David Deutsch, Vera Schaefer and David Lucas from Oxford's Department of Physics, Simon Benjamin, Tyson Jones, Natalia Aries, Jason Smith and Andrew Briggs from our Materials Department, Chris Timpson from the Faculty of Philosophy, Jamie Vickery from the Department of Computer Science, and Ali El Kafarani from the Mathematical Institute. And my thanks again to you, listener. That's it for this one-off special episode of Futuremakers. We'll be back in the autumn for Season 2, which is going to be all about how we can tackle climate change and build a sustainable future on planet Earth. I'm Peter Millican, and you've been listening to Futuremakers. Thanks, guys. Good show today.
No worries. Actually, this one reminds me of that podcast we were telling you about.
Which one?
It's the End of the World podcast with Josh Clark. It's really interesting stuff.
Yeah, we've both been listening to it. It's about the ways humanity might accidentally wipe itself out with the technology we're developing now.
Really? So artificial intelligence, haphazard physics experiments, that kind of thing?
Sure, and even how an artificially mutated virus could escape a lab and create a global pandemic.
Serious stuff then.
Yeah, and it also covers some fascinating science, and it's got a beautiful score and really cinematic sound design.
That's an original score as well, I think. There's all sorts of stuff in there. Spacecrafts trying to navigate interstellar space.
Yeah, there's a bit on the far future where humans have evolved into a post-biological species who live in digital form.
A post-biological species? That sounds a bit like Ben already. Where can I get that?
I listen on Apple Podcasts. You listen somewhere else, right, Steve?
The iHeartRadio app, but you can get it wherever you get your podcasts. Or look out for the EOTW Josh Clark hashtag on social media for more info.
There are 10 to listen to as well, Peter. So that's your weekend sorted.
Thank you. I'll look forward to it.
We asked Al Murray, the pub landlord, if he knew scientists may be on the verge of making quantum computers that can do insanely complicated calculations in a split second, possibly by trying out all the answers in zillions of parallel universes.
No, you're making it up. That surely doesn't exist.
We're sure you must have a question about the technology that holds such revolutionary promise for the advance of civilization.
To find out what quantum questions Al asked, listen to Stupid Qubit Quantum Computing for the Clueless, where we'll also answer the questions: what the photonic muck is a quantum computer, do they really work in parallel universes, and could they be set to achieve quantum supremacy? Available via your favourite podcast provider or direct from stupidqubit.com.
Qubit.